This video is finding confidence interval for a difference between two means.
Okay, a very good day. We are going to continue the confidence interval for difference between two means. We are focusing on the case now birth sample size and birth variance are not equal and birth sample size are also less than 30. Hence we use the t distribution table. So the learning outcomes is actually finding confidence interval for difference between two population mean where birth sample size are less than 30 and not equal. Both population variance are also not equal. So if both population variance are not equal, we no need to calculate the pooled estimated variance as p squared, and as in the previous two videos. Okay, we recall back still. When both sample size are less than 30, we use a t distribution table, where we got four cases where the first case are n1 equal to n2. However, the both population variance are not same, and we use this formula, where it's t alpha over 2 nu, and this is square root of the s1 squared divided by n plus s2 squared divided by n. Nu is n1 plus n2 minus 1. If both variants are the same, we got to calculate the pooled estimated variance using this formula, and then s1 squared replaced by the sp squared, s2 squared replaced by sp squared. The third cases are actually same with the second cases where both population variants are same. So s1 squared replaced by sp squared, s2 squared replaced by sp squared. However, the third cases both n1 not equal to n2. Now we got the last case where both sample size and both population variant are not the same. Hence, sp squared, we no need to calculate sp squared, remain as s1 squared, s2 squared. However, the nu in the first three cases is calculated using n1 plus n2 minus 1. However, for the fourth case, we got to calculate the degree of freedom nu using this this formula. This formula. So you see case 1, both sample size same, nu n1 plus n2 minus 1. Case 2, both sample size equal, both variant equal, nu still the same thing. Third case, both sample population variance same, so the nu still n1 plus n2 minus 1. Only the fourth case, both variant not same, both n not same, we got to calculate the nu using different formula. So today, this video will focus on the fourth case of the t distribution. This is example 9, where both sample size are equal, both sample mean are mean or sample variant are not the same. So we use the first formula of the t distribution table. Now we are going to change n1 to n2, we are going to change n1 to 10. Reconsider example 9. Population variant are not equal. Sample size for 1 change from 15 to 10. This is the fourth case of the t distribution table here. So this is the information. Variant for first sample, 0.3, second sample 0.44. 0.44, and 110 and 215. Mean for sample 1 8.69, sample 2 8.51. So since both sample size are less than 30, we use a t distribution table, and since both variants are not the same, no need to calculate the pooled estimated variance as p squared. However, both sample size are not the same, Okay, we use the case 4 for the t distribution. Okay, we use this formula to calculate the nu. Okay, you can calculate by yourself, and we get it is approximately equal to 22. So now we got to recalculate our t alpha over 2 nu. Okay, so before that, now n1 plus n2, oh sorry, nu already calculated is 22. Okay, alpha still 95 confident interval. Okay, so the difference is, if the third cases n1 plus n2 both variant are the same, the nu will be total 25 minus 2, which is 23. But this example where both population variant are not the same, we got to calculate nu using this formula. We get 22. Okay, 22 nu is 22 alpha over 2, 0.25. We get the t alpha over 2 nu is 2.074. Yeah, right. Let's see the value here. 2.074. Okay, we use back the same formula to get the lower confidence limit, where the A is the mean sample 1. Okay, we calculate the same value 8.69. B is a mean sample size 2, 8.51. C now, C is a T alpha over 2 nu. In the previous video, sample size 1 10, sample size 2 15, so 25 minus 2 is 23. So it's 2.069. Now because both population variant are not the same, we got to calculate nu using this formula. We get 22. So the value at alpha over 2 0.025 is 2.074. So 2.074. So I change the value to 2.074. D, this is a previous pooled estimated variant. Then we got to replace back with now, because the both population variant are not the same, we got to replace the D by the population variant, which is 0.3. And number of sample for population 1 still 10. F is a variant for population 2, 0.44. M is a sample size for population 2, 15. So I get the value. Because this is a plus, the formula for upper confidence limit 0.6852. Search back for the lower confidence limit. Then we calculate A 8.69, B 8.51, C 2.074, D is 0.3, E is 10, F is a second population variant 0.44, M is the sample size for population 215. So you get negative 0.3252. Where this is a case of t distribution table, where both sample size not equal, both variant not equal. You got to calculate the nu using this formula. And then we obtain this confidence interval. Hence, we are actually 95% confident that the difference between mean diameter of steel rods manufactured by machine 1 and machine 2 is between negative 0.3252 centimeter and 0.6852 centimeter. Then we recall back. Basically, now we are focused on the fourth case of the t distribution table, where both sample size and both population variance are not the same, we use T alpha over 2 nu, where the nu you got to calculate using this formula, and then put the S1 squared, S2 squared, N1, N2. Okay, basically I use this formula in the calculator. I will use this formula in calculator no matter you have T alpha over 2 or Z alpha over 2. So if the second and third case where the both variants are same, S1 squared and S2 squared you replace by the SP squared. Nu is N1 plus N2 minus 1. And then you calculate the for SP squared using this formula. Okay, the formula still applicable. First case, DF S1 squared, S2 squared, E and M can replace by the N lah. So A, B, the same C, okay, T alpha O2 nu. Okay, so with this, thank you for your attentions.